Hello everyone, reporting today for Fun Robotics Network. I'm Abbas, and with me here is none other than Team 11260, Up-A-Creek Robotics. They have just been absolutely unbelievable this entire season. Pretty much the first Clipbot, the most successful Clipbot, list goes on and on. Just insane. I can't wait to jump into this on Behind the Bot. Okay guys, so the first question is obviously, why Clipbot? I think every season you consistently push the bounds of what's being done in FTC. Why did you choose the Clipbot as that architecture this year?
Yeah, I think what we really wanted was a challenge. So this is the kind of thing we were kind of thinking about it and theorizing as soon as the game came out, because there wasn't actually any rules about possessing more than one clip, but we thought that they were going to make it illegal, right? And then 2 weeks later, they released the first game update, and it became explicitly allowed. The robot can hold as many as you want, and you can make your own specimens. And from there, we realized that this is really something we want to do, not just because it's a very strong strategy and it saves us a lot of time on our cycles, but also because it's something that would make for a really memorable and fun season.
Yeah, absolutely. And from that cycle time perspective, really quick, in your initial brainstorming and strategizing, what sort of improvements were you seeing, like just from like general points or percentages? Talk to me about that.
I think it really helps with the cycle time because you don't have to move it all, and where that really shows improvements is how you're able to do these cycles concurrently. So we're able to have, especially in autonomous, our intake is running at the same time as our depositor is running, at the same time as our clipper is running. And since we're not moving, we can be intaking and depositing almost at the same time, and that really helps a lot, especially in autonomous.
Awesome, yeah. And so we're gonna start with the intake, then talk about the clip loading mechanism, then the clipping, then the deposit. So let's jump into the intake. Lots of degrees of freedom there. Walk me through the general ones, and then I have a bunch of specific questions.
Yeah, so our intake has 1 degree of freedom. That is the extension. This extension is powered by a car antenna actuator, which is a nylon rod that pushes through these telescoping tubes. You can see it's over there. And then we have a turret, a 4-bar pivot, and another degree of freedom on the intake itself to pick up from any orientation. And yeah.
So about that car antenna, just going back to it briefly, why? Was it a space concern, just some mechanism you really wanted to try out? Is there a huge benefit to it?
I think it's worked really well for us, and it is really efficient with the space. So this is the entire assembly of what it looks like. It connects to the motor on the end here, as you can see. And so this is really compact with the actuator. It means that our extension can be very compact. And all of the actual mechanisms is back inside of the robot, and that works better with how we were designing.
Yeah, now jumping into the bearing and turret situation, what's the basis of your turret right here?
I would say, we have a large bearing on the bottom here. It's powered by an axon servo underneath. You won't be able to see the bearing, but you can see the servo is connected to a servo horn inside of there, and then
yeah, and now I also see you have the 4-bar mechanism over here. So why the 4-bar as compared to, we've seen a lot of belted designs, things like that, but you were able to get the range of motion with the traditional 4-bar right there?
Yeah, exactly. So we had lots of different things. Originally, this was just a bar that would extend to the intake as a pivot. But the issue with that is that it would extend out of the side of our robot, and we thought that would be very dangerous, especially since we have a really light intake. So what we did instead, we use this 4-bar. It allows us to go down to the right height and extend up and retract within our robot while still staying under the top bar.
Awesome. Yeah, now jumping into the claw right there, I see a lot of little alignment mechanisms here and there. Walk me through how your claw works.
Sure. So our claw is picking them up from the inside, like I mentioned. It aligns with these claw shapes. These are something we've tried and iterated on a bunch of times. Right now we have these kinds of triangle things that will center to the inside of the block and be able to spread to catch the inside.
Yeah, and as far as sensorization goes, in the claw alone, is it like beam brakes, anything like that, or no sensors needed?
We used to use a beam brake sensor, but we found an alternative is a stall detector circuit that we run inside of our robot. And what that does is, as it is opening, as soon as it fully opens in order to grab one of the samples, the servo will stall, and with that detecting that it has stalled, we're able to know whether or not we've intaked a sample, and we can use that to automate our autonomy.
Yeah, absolutely. Now, jumping a little into the software behind all of this, starting with loop times, I feel like that's got to be a pretty big concern when you have all of these things running in parallel. Anything you want to talk about there, how you sped them up, made them very consistent? Talk to me about that.
Yeah, so we structure our code as few separate subsystems that work independently, and each one has its basically runs in the background, a constant read update. The big thing about the intakes for loop times was vision and getting those loop times down. Our loop times, we use Up-A-Creek and OpenCV, and that's kind of that's really the big fault on our loop times, as well as I2C channels. So to get those down, bulk reading has been a big effort. We do that, and then otherwise loop times, they're mostly in the vision system.
All right, yeah, so let's jump right into vision. We've seen a lot of limelight usage this year, not you guys though, so walk me through the camera you're using, why you used it.
Yeah, we opted not to use limelight because we really wanted a big FOV with a lot of control over our vision system. That is a 120-degree field of view global shutter web camera. And our vision system, we have a picture of kind of our pipeline up here, right up there. That shows how we take the image, we undistort it. That's a really big step in vision to have nice geometry so you can find things. We then take perspective transform or homography. And then from there, each season is a lot of minute OpenCV kind of fiddling around, find what's the best way you can get a consistent detection. And the big thing there is to get your loop times down is try to do bulk operations when you can and isolating your regions of interest. So we do, I think, about 3 steps of like finding contours, then doing edge detection to really narrow down what we care about before we do more expensive operations like temple matching.
Yeah, and so now vision, I feel like the concern is always you have it working fantastically at home. Even if you have a conference room at Worlds, you have it working great there. Then you get onto the field and suddenly everything's not working anymore. But I mean, you guys have hit that 9 specimen, 10 specimen pretty much every single match. So how have you maintained that consistency? What can teams learn from there?
Yeah, a big thing we started with was in the calibration time at the start of the tournament, we took pictures with our camera and saved them to our robot, and then we downloaded it onto a computer so we could keep working on vision outside of our calibration time. That was a big help. And then another thing we do is when we're filtering, two other big things that help with lighting issues are doing gradient filters like a Sobel filter, or there's another one, I don't remember the name. We use a Sobel filter. And the last thing being for whenever you're using color filters and like thresholding, we calculate what are our thresholds based on a normal distribution of the color we want rather than any specific HSV bounds, and that also helps make it a little more robust.
Absolutely. Okay, let's jump into the clip loading mechanism. Walk us through how it works in general, and I have a ton of questions after that.
All right, so our clip loading mechanism uses this clip claw here that has the capacity for 9 clips. At the beginning of autonomous and also at the beginning of teleop, assuming our autonomous fully hits everything. We pick up the clip, we load the clips onto the wall, and our clip picks them up off the wall, all 9 at once, and it grips them with this servo and cam.
Okay, got it. And I feel like one thing here, you're holding on like just to that thin, web or neck of the clip. Alignment and consistency and accuracy in that must be a challenge. How did you guys address it?
Yes, so one thing that we do is because of our cam, we're able to open the claw very wide, as well as getting lots of clamping force. So we're able to open it wide, which gives us front and back tolerance. We also have tuned the distance of this side panel from the clip to make sure that when we drive right up against the wall, the distance is correct. And then we also drive slightly sideways to make sure all of the clips are aligned this direction in the clip.
Yeah, that makes a ton of sense. Now, going through the clipping itself, once you have them all loaded here, how does this mechanism work?
Yeah, so starting over here, we have a triangular gripper that has a piece of foam on it. That piece of foam acts as a passive gripper. There we go.
With that,
and that allows us to slide this whole mechanism to any position of the clips along here. Another feature of this gripper is that it's coated in Teflon, which allows us to easily slide the clip out without actually opening it much wider. Next, we pull the clip back to here and reseat it by pressing it up against this reseater mechanism here. That makes sure everything is perfectly aligned for when the clipping sequence actually starts.
Got it. Yeah. And now talking about sensorization here, is it all encoder based and just using the servo encoders, motor encoders if you're using any motors there, or are you also using distance sensors, beam brakes, limit switches?
Thank you. So we started handling mostly with just what we already knew about our clip count. In the code, there wasn't any sensors, but as we worked through reliability, we found that it was nice to have this limit switch in the back, and that basically tells us whenever our kind of the back pinion here hits the back end, you know that it's there, and that knowledge kind of lets us stagger our different mechanisms so that they don't interrupt.
Awesome. Yeah. Now you have the clip on, you have a sample in the robot. What's next?
Yes, so the sample will transfer from the intake to the depositor in this area here. It will slide in. The depositor will press down this lever here, which allows the intake to slide in past this wall. Then it transfers to the depositor, and then the depositor lifts up. The depositor lifts up, and after the transfer, and this wall goes up, making sure that the sample is held in well there. Then the clipper mechanism just slides over it, and it rotates. It's designed to rotate around this center, or this clip. The center of rotation is right around this clip, which it doesn't move the sample too much. It reduces any motion on the sample as it's clipping. So then it just slides and clips, and then it pulls back. The second feature of this bar allows it to easily remove itself from the. This second function of this bar allows it to easily pull the clipping mechanism out of the clip, which gets everything out of the way, so the depositor is able to then score the completed specimen.
Yeah, and I feel like one thing, as we can hear from that stat there, that people thought would be difficult with the clip bots is that torque you need to just really seat that clip in. Is that a challenge you guys faced? If so, how did you work around it?
Yeah, so one of our first priorities as soon as we started designing the clipper was get a working prototype to prove this is possible to do. Originally, I was assuming we would need some sort of either linkage that gives us a mechanical advantage or gearing of some sort. But pretty quickly we realized that even a go build a torque servo actually has enough torque to clip the specimen. However, to increase reliability, we increased to the highest torque servo that we basically had available to us, an Axon Max, and we have had we had some slight issues before, but those have all been fixed, and the torque that this servo provides is plenty to clip without any extra gearing.
Okay, and I think the last topic here is going to be the depositor onto the specimen, or onto the chamber itself. I see lots of moving components every time. So yeah, why? Is it just like packaging? You got to work around all the components of the robot? What's going on there?
Yeah, exactly. So the depositor is the mechanism where we definitely spent the most time looking at the packaging and how we could fit it. So instead of having a depositor that's symmetrical around the center of our robot, for instance, we have something that's off to the side, only one set of vertical slides. And that's because compared to the intake and other mechanisms like that, those require a lot of precision. The depositor does not require a lot of precision. And so we're able to make it pretty simple like that.
Yeah, and I'm really interested in this mechanism right here with that ellipsoid. Walk me through the cam, why this profile, things like that.
Right, exactly. So the cam is something we actually use on all three of the grippers on our robot. So we also use it on our clip claw and our intake gripper. What this allows us to do is it allows us to use much smaller servos to actuate these claws. So if you can see from this side, we use a micro servo right here, and this makes it much lighter. It makes it requires less current, and the reason that that's able to work is because you get a lot of mechanical advantage from the cam when you're at this horizontal position, so you can have a very high grip strength without compromising additional current required in your servo.
Awesome. Yeah, Up-A-Creek, thank you guys so much. I mean, you guys have just built a beautiful machine, and the programming behind it is also so complex, and it's really impressive seeing how it all comes together. So, reporting for Fun Robotics Network, I'm Abbas, and this is Team 11260, Up-A-Creek Robotics. Thank you.